Okay, I'll start the session. Today it may be somewhat boring and somewhat interesting at some times, but we are going more and more into technical details. Today we will be looking at various coordinate systems that most of them were used in astronomy, and many of them are used in radio astronomy as well. Also, radio astronomy has something extra for antennas and related electronics. Some coordinates related to the antenna positions and some other antennas has been compared with a reference antenna. So we require some extra coordinate systems. And also there are conversion of coordinates. So we will go through this in somewhat details, but I will not give any worked out examples. Some formulas I will give here, and if you want, you can actually do it on your computer. If you want to convert one coordinate system to another, you can take some values and you can do that one. Now this is what I will be doing, and this is coming in this part, that is Introduction to Radio Astronomy. We have two parts in this, 1 and 2. The second part I will talk when I start, but I can summarize it as it will consist of the basic imaging techniques. Not imaging techniques as such, overall radio astronomy as such, an introduction and introductory basic techniques that you require in radio astronomy, including imaging. So I will go to this one, and there are about some 48 or 50 slides. So I'll try to cover it up in 2 hours. Okay, so here we go. The origin of radio astronomy, you can say, is due to one radio engineer called Sir Carl Jansky. He was working in the Bell Labs, and he was trying to locate some sources of static noise that interfered with radio reception at 14.6 meters and 10 meter wavelengths. Some of this noise he found to be originating from the nearby thunderstorms, while others were from distant sources. So these two noises he was able to detect the sources, but also he listened to a faint hiss which he was not able to relate to any one of these, and he didn't knew where from it is coming. So he was experimenting on this, and he kept recording the data. Over a year, he noted the crests and troughs of intensity of this with his signal. Now here is the record. You can see this is the time axis, and this you can say amplitude. Now he noted that in the hills there are some peaks occurring, and these peaks were separated roughly about 22-minute intervals. Now when he located the direction of this, he found that the direction of this is changing. So what he says is, changing direction of peaks about 22 minutes intervals indicate that the source is not stationary with respect to Earth, and which means that the source is from some other origin, that is the extraterrestrial origin or whatever it is, but it is definitely not from Earth, because he was not able to find its direction. Now there are some astronomical units which we have borrowed from general astronomy, and some of the units we have borrowed from communications, engineering and all. Both of these are used in astronomy, radio astronomy. So here these units you can find out from the internet also. Generally one astronomical unit, it is the average distance between the Sun and the Earth, that is 150 million kilometers. Average distance means over 1 year you can calculate the average distance because the distance from the sun to earth will vary because it has a elliptical orbit, but this is the average distance. Now there are other units like parsec, which we have to explain a little bit about this. See, one parsec is equal to 3.26 light years approximately, and 1 light year, I think you know that is the distance covered by light when it travels for 1 year. That is the light year, and this is roughly equal to this much astronomical units. 1 astronomical unit is 150 million kilometers. Now this is parsec converted to kiloparsec, that is 1000 parsec, and this is megaparsec, that is 1 million parsec. Then we have solar flux unit. The solar flux unit is everything that we see on Earth is actually a result of some electromagnetic waves. Or I am talking about astronomical objects. We cannot go there, but we have to know about that by understanding the radiation from it. So we need some units to measure these radiations. And sun also emits in radio, that we will see later. So for measuring the power per unit area per unit unit bandwidth, we call this as 1 solar flux unit, that is equal to 10 to the power minus 22 watt per meter square per hertz. Then there is one more unit called Jansky, named after the inventor of radio astronomy. As 1 Jansky is equal to 10 to the power minus 26 watts per meter square per hertz. It is still smaller than 1 solar flux unit. Now we go to the somewhat bit of explanations and details about the coordinate systems. So before that, we need to know how these things are. I think many of you may already be knowing this, but still I will try to explain it for those who do not know. This is our Earth. If you see this picture, this I have borrowed it from internet. I don't know from where I have taken it, and I couldn't acknowledge that. But anyway, I think I think he will not be annoyed if I show this figure here. But it may be somebody's copyright. I don't know. So this is our Earth here, and if you see the sky from the Earth, you can consider it as a shell. This is a shell. And this shell has got almost infinite radius. The radius from the center of the Earth to the shell, you can consider it as infinite. So you can consider the entire sky to be a shell-like object enclosing our Earth. And the Earth moves along this axis, rotates along this axis, and so you will see that the stars are going from east to west direction. As the Earth moves from west to east direction, you can see the celestial sphere to be moving in the opposite direction. Now I will read this one. All celestial objects like stars and galaxies appear to lie on the surface of this sphere known as celestial sphere. 2 angular coordinates are required to specify any point like star. Okay. Now we don't know what is the distance from the Earth to the object. Normally, if you want to know a position of the object, for example, if we take this point, we can measure this angle, we can also measure this angle, but we cannot measure this distance. This is unknown. So in astronomy, we generally use 2 angular coordinates, not the distance. The planes passing, intersection of a plane passing through the center forms the great circle. Now this entire thing has a center, which is the center of Earth, and if you cut this one using a huge plane, you just pass it through this one, and so that the plane touches the center of the Earth. Then it will draw a circle on this shell. That is where it will cut, and that circle is called a great circle. Now, if you cut the this shell slightly above or below this one, so that it doesn't touch the surface, but the earlier plane and the current plane, if you keep them parallel, then you will see some smaller circles on the shell, like this one. This one you can see. This is smaller than this one. So this may be called as smaller circle. Similarly, you can actually cut the sphere along this direction, and you get these things, these kind of things. These are like longitudes and all. Now, there is one more thing that if you want to measure some position and all, you need a reference point. So, people have tried different reference points over the centuries, and one reference point which people use even now, and that is very popular, that is called the vernal equinox point. How do you know that? If you have this earth like, we have our earth like this, this is our north pole and this is our south pole, it is rotating along this. Now, if you see the sun as observed from earth over the years, you will see that the sun revolves, actually the earth revolves, we know that, but from the earth it appears that the sun is revolving around the earth in a plane which is 23-degree inclined. So this plane is called the ecliptic plane. And also the celestial sphere, we have seen earlier, that will rotate in synchronism with the earth rotation, not in synchronism. The celestial equator will rotate in synchronism with the earth, because the celestial equator is formed by extending the earth's equator on the shell. So the line that it produces, that is called the celestial equator. The shell will be moving in opposite direction, because we see the stars to be crossing our position. But we call this imaginary circle, which is located on the celestial sphere, to be the same as our equator extended to it with using a plane. Now this ecliptic plane and the celestial equator will cut at 2 points. One you can see on this side, the other is on the back side. Now where you can see that this is the southern part and this is the northern part, northern hemisphere or whatever you say. So when the ecliptic crosses from the southern hemisphere to the northern hemisphere and it cuts the celestial equator, the point where it cuts, that is called the vernal equinox. This is related to the equinox that takes place, we know that during which days and night relationships like equal and all, whatever it is. It occurs 2 times a year. And if you see there is one more equinox that is on the portion which is hidden, that is the autumnal equinox. Now for vernal equinox, we usually represent by this signal, this symbol. This is called auris. This is called some astrological sign. So this is the starting point of that. And for astrological point of view, also in Western astrology and all, they use that as the starting point of auris. Now I will read it here. Consider the Earth as the center of universe. From Earth, the Sun seems to revolve around it in a path called ecliptic. The celestial sphere seems like a shell rotating around the Earth on the north-south axis, extending the equator of Earth on the celestial sphere forms the celestial equator. Okay. With these ideas, we can form different coordinate systems that we use. The first is we make a general coordinate system. As we have seen that we require 2 great circles perpendicular to each other for as the measuring point, reference point from which measurements will be taken. So it means that there should be a fundamental great circle like this. and there should be a fundamental great circle in this direction. This is called fundamental secondary circle, whereas the one that actually cuts the polar axis, that is the fundamental great circle, and that which is parallel to the polar axis is called the fundamental secondary circle. You can see it marked here. And where they cut, you are free to choose these two circles. This one you have no choice, because this circle will be unique, whereas these circles, they are not unique and you have to place it somewhere. So this is the, we consider this as the reference point. This is O. Now, also I forgot to mention that if you have any circle which is parallel to this fundamental great circle, they will be smaller, as I said earlier, and in this case they are called phi circles, because phi is the other coordinate or variable with which you measure the position of the object. Now here, if you have a star or something like that positioned at x, then you will require this phi along this direction. That is, this is the angle. This angle is phi, and also you require this angle. This angle. This is theta. So with these two, you can say that the object is located as phi is equal to this much and theta is equal to this much. Now I will read this one. Consider a point x on the celestial sphere. The coordinates of x are theta is equal to OY, this one, measured along the fundamental great circle. So this is it. And phi is equal to yx, measured along the secondary great circle. The loci of the constant phi are small circles parallel to the fundamental great circles known as the phi circles. In this diagram we call this phi circle. In other diagrams we will call it delta circle or diurnal circle, any such things depending on what is the value of this one. The latitude and longitude of any place is a good example of spherical coordinates. So you can, for example, for the Earth, you can consider this as North Pole, South Pole, and these are the longitudes. And these circles are the latitude circles. Now we go to the local equatorial system, that is called H and delta. H comes from hour angle or something like that. Now this diagram looks a bit complicated, but I will try to simplify it. You are exactly not on the celestial, not on the North Pole. Our position may be somewhere on the equator or some other place. So we will have a local plane. This is the local plane, this one. This is the local plane on which this is parallel to the ground, you can say, and you have east, west, north and south of this. Whereas our axis of rotation, that is the North Pole and South Pole, that may be along this direction. And when we extend this, it will hit the celestial sphere at 2 points. One is the celestial North Pole, one is the celestial South Pole. So, and this is the celestial equator, because this has to lie perpendicular to this axis. So now you can see the diagram is not that very complicated. And then if we want to measure any object on the celestial sphere, for example the point S dash, if we have to measure, then we have to measure it along this direction, which is one angle, and along this direction, which is another angle. This is called the hour angle and this is called the declination. Now you can actually relate this circle with time, because this 360 degrees rotation will take place in 24-hour time, or to be more accurate, you can take the sidereal time, which is 23 hours 56 minutes and some few seconds. So that is the time taken for any, if an observer looks into the sky at a particular point, for example a very distant star, and after this much time he will be able to see the star at the same position. So our 24 hours is because that Earth also rotates and revolves around the sun. So there is some little bit of complication which if you see because of which our time is slightly different from that time. But that time is more correct way of measuring the time, sidereal time. So I will just read this one. The plane of Earth's equator forms the celestial equator. Small circles parallel to the celestial equator form the diurnal or declination circles. So this is the declination circle because this is the declination angle. Our circles passing through the local zenith Z and nadir N dash and celestial poles in the celestial meridian. Okay, nadir is the point below us, and Z is the zenith is the point just above us, that is perpendicular to the plane in which we are sitting. So these are called zenith and these are called nadir. Our circle passing through the local zenith Z and nadir N and celestial poles. Okay, yeah. Our circle, the celestial meridian, we can call a local meridian, geographically you call it a local meridian. If you say what is the local time and all, they are related with the local meridian. So local meridian is the meridian which actually goes touching our zenith. That is the local meridian. If I move to a different place, then the meridian will be different. But because then our zenith will be different. Now from this diagram you can see if H1 and H2 are hour angles of a star observed simultaneously at two places having geographical longitudes L1 and L2 respectively, we have H2 minus H1 is equal to L2 minus L1. So this is the hour angle of a star measured at point 2 and this has at point 1 is the same as the longitude at point 2 minus longitude at point 1. So it's just relating the hour with the longitude. Now we go to the universal equatorial system. In the previous equatorial system, local equatorial system, we used the local coordinate as the reference point. If you see this one, this is the local meridian you are using as the reference point and from which you are calculating this. But in this case, instead of using a local meridian, you use this point, this auris, point auris, where you can consider it as the starting point and you measure the angle. So in this diagram you can see that this is the point which you want to measure. Here you have a declination and here this angle alpha may be called as right ascension. And if you see this plane, the ecliptic plane, and this is the ecliptic plane, this is passing from, this point is passing from celestial south pole towards celestial north pole. So this is this auris. And we consider the 0 hour circle from where we want to take measurements, that will be starting at this point. Now as we move on, we measure these points, not our angle, I mean right ascension declination, by measuring these angles, alpha and delta. And this angle between these two, that you know is the obliquity of the ecliptic. This is 23.5 degrees. So I will just read it now. This is similar to the local equatorial system, except for the reference point on the celestial equator is fixed on the vernal equinox auris, point at which the ecliptic crosses the equator from south to north. Right ascension and declination, alpha delta, are used for preparing permanent star charts. So in most of the star charts that we have, like Cambridge, many charts are there actually. Some alphabets are used for with them to specify which chart it is, symbolic names of different things, starting with M, S and many other ways that you can have a look at the star chart and you can see that one, the Cambridge, something like that. Now, as an example of this equatorial system, here we present the reverse radio map of galaxy. To pass you some information, Reber was the first accepted radio astronomer. So he was an experimentalist and engineer, and after he found Jansky's discoveries in his papers, he built his own radio telescope. It was a single dish, and he plotted the Milky Way at a frequency of 160 megahertz using the equatorial coordinates. And he was the first radio astronomer, because Jansky only discovered the phenomenon that radio waves come from outside world, but he was the first person to make the charts. So this is the intensity distribution. As you can see, these are contours, and these are the declination. This is the declination angle, and this is the right ascension or hour angle, you can say, and this is the other side of it. So it is from 2 to 14 hours, and this is 12 to 0 hours. So you can see that this is our Milky Way galaxy, our own galaxy, and having a different distribution of radio intensity. So I'll just read it. Reverse radio map of galaxy at 160 megahertz. Contours are in equatorial coordinates and are more or less coincident with the Milky Way, adapted from Reber. In 1944 he published it. Now we go to the horizon or alt-azimuth system. Of course, this is not an astronomical coordinate, because okay, the difficulties are obvious. You will know it when you think about it. This is for using it locally, because we don't go to the celestial sphere, and for most of the things that happen on Earth, we may record it with this. The difficulty of using celestial sphere recording is that there are variations in these coordinates, and it is difficult to make out. The mapping becomes difficult. Now, in this system, this is the plane in which you are sitting. That is the plane of Earth. You are at the center, and this is the east-west, south, east-west, and these are the south and north. This is the zenith, and this is the nadir. And you consider your prime vertical at the east. Now, if you have a point on the sky at S, you can measure it using this azimuth and this as elevation, A and E. Now, the reference point where the 0 point occurs, that is usually at north, or in some systems they take it as south. So north is southwest, and then north. It covers 360 degrees, or southwest, north and east and south. So the people may use south as well as north as a reference point for this azimuth axis. Elevation axis is the angle as you can measure from the ground. Now, I'll just read it. Any great circle touching the zenith Z and the nadir N is known as the vertical circle. So here is a vertical circle. It is touching the zenith and nadir. A vertical circle joining the east and west is known as the prime vertical. This is a prime vertical because it is joining east and west, this one. Small circles parallel to the horizon are known as altitude circles. Again, this we know that this is the elevation or altitude. So any circle parallel to this will be altitude circle. Azimuth angle is A and altitude angle is E. This is actually, it should be symbolically like this. I didn't use proper fonts, so I got in this shape. The origin can be either north or south. It is generally very useful for mechanical positioning of a telescope antenna. Now we go to the galactic coordinates, but it may be easier to understand it this way, and then we go to the actual diagram. Now this is a artist sketch of the Milky Way. I am talking about this figure. So this is the core of our galaxy, and there are several arms, 3 or 4 are there. I don't remember exactly how many are there. And the distance from here to here is about 22 kiloparsecs or something like that. And our sun is located from the center of our galaxy to be around 8.5 kiloparsecs, if I remember it correctly. And the central zone of the galaxy, that is Sagittarius A, that is called the Sagittarius A, where a giant massive black hole is sitting and forms the main gravitating origin. I mean, it keeps our galaxy intact. Of course, the gravitation is dependent on many other things, many other objects are surrounding it. As we move away from it, we will see the gravitational pull. Okay, but anyway, this massive black hole is responsible for what we call this as Sagittarius A, that particular point. Now, when we construct when we observe galactic objects, we require a different coordinate system, because the other coordinate system that we described earlier, they may not be very, I mean, they may become very complicated. So to make things easier, we use a different coordinate system. So if you stand on the sun and with your head facing towards the north, that is on the northern hemisphere, then and you look at the galactic center, and that you consider as the origin. In this diagram you can see, you are standing over here, and this is the center of the galaxy, and this is the origin. And if you see an object on this side, you have to have 2 coordinates. One is the longitude, another is the latitude. So here you can see that this is the latitude, this is the galactic center. So not longitude, latitude, they are called actually galactic longitude and galactic latitude. So I'll just read this one. Galactic coordinates use the sun as the vertex. Galactic longitude L is measured with reference to the direction of center of galaxy. Galactic latitude B is measured between the object and the galactic plane. Now we go to the actual diagram. So you can see that our position is here, and this is called the galactic north pole. This is just, if you increase it to infinity, this point on the celestial sphere will be the galactic north pole. This point will be the galactic south pole. And from here you are looking towards Sagittarius A, that is towards the galactic center. And you can calculate this one. This is the galactic longitude, and this is the galactic latitude. Now, as this is the galactic latitude, then any circle that will be parallel to this are called the galactic latitude circle. And this is the point of the object which you are taking measurement. I'll just read it. The great circle formed by extending the plane of the Milky Way is the galactic equator. The poles are galactic north pole and galactic south pole. The great half circles between the poles are the galactic longitudes L. Small circles parallel to the galactic equator are galactic latitudes B. Useful for studying the problems related to the structure and motion of the Milky Way. Okay. Now, I'll read this one. The galactic center is the rotational center of the Milky Way galaxy. Because of interstellar dust and along the line of sight, the galactic center cannot be studied at visible ultraviolet or soft X-ray wavelengths. You cannot penetrate through this dust to look into the center in these wavelengths. But in radio you can actually see what is there. So this is a radio image. The radio image of the region surrounded by the radio source Sagittarius A, that is the center of the galaxy. The color code runs from red for brightest regions through yellow, green and blue for faintest part. This they are talking about how this is not the actual color, because you cannot say what is the color of radio waves. So this has to be a pseudo color. So it is only talking about that which side it is higher frequency, which side it is lower frequency, or which side it is lower wavelength, higher wavelength, and so on. This talks about this one. And then it also says the area shown is about 180 light years across. So this area, or this should be a square like structure. I have misfitted it. It has turned out to be rectangular. But this one is something like 180 light years across. And these are the various things that is inside that one. Pardon? Yeah. Yeah. See, that depends on the scattering properties that we discussed in the previous lecture. Okay. So it depends on the wavelength. So as the size of the particles that is coming in the way, even if you talk in a general sense, you will see that if it is larger, then it will affect at longer wavelengths. But if it is smaller, then it may not affect the longer wavelengths at all. So the radio waves can penetrate through that. Yeah, they are dust particles, so they can always penetrate through that. They are very small. Now we go to the ecliptic coordinate system. Again, these are all similar kind of things. There is no much difference except that in which plane you are choosing, and there are two angles you have to choose. Now this one, this reference point is with respect to this point itself, that is the Auris point, but you will be measuring along the ecliptic plane, and this is lambda and this is beta. A source here will be measured in these two angles. In equatorial system, we were doing it considering this plane as the fundamental great circle, but here it will be like this here, and we call this as the ecliptic north pole and ecliptic south pole, whereas celestial north pole and celestial south poles are here, and these are a separation of about 23.5 degrees or something like that, the obliquity of the ecliptic. So I'll just read it. The ecliptic forms the fundamental great circle with the vernal equinox gamma as its origin, this one. The great half circles joining the ecliptic north pole and ecliptic south pole, this one, are the celestial longitudes. So these things are the celestial longitudes. Longitude of a star is lambda angle gamma CF. Angle gamma CF, this is the longitude. We have several such longitudes like this, and this angle is the longitudinal difference. And its latitude is beta, this one. This is useful for studying objects within the solar system, within our own solar system. This is generally used for amateur astronomers and all. They may be using this. Maybe others also, I don't know. Now this is something, this coordinate system may be only for radio astronomy, this XYZ coordinate system. The diagram looks very complicated. So let us first talk about it first. While doing mapping, or I think here in this audience, or maybe one or two have done the made radio images out of radio data. But what I want to say is that in that, or you may see that there is a thing called reference antenna. See, for example, in the GMRT array, you have a reference antenna in the central square, some antenna, and all other antenna positions are calculated with respect to that reference antenna. Now we consider here two antennas. One we consider as the reference antenna, and another antenna we call it as a test antenna, you can say, or whatever it is. And we want to relate these two using the declination and hour angle, and also has to be related with the local XYZ coordinates. Now you consider this as the reference antenna. Here you construct your XYZ rectangular coordinates. This is the celestial equator on that one, celestial plane. In this you have to form this one. And your antenna, the other antenna may be slightly higher or lower at some place, somewhere, having a different meridian. This is the meridian for this one. So the position vector joining these two antennas can be found from this this particular element square plus this particular element square plus this particular element square, forming this one, this parallelepiped. So this is what it is. This modulus of the position vector d is equal to x square plus y square plus z square square root. And you can relate this x, y, z with the hour angle and declination. D stands for declination, H for the hour angle H. So this is the meridian of the reference antenna, and this is the meridian of the antenna test antenna. So this the angle between them is H, and also the position of this antenna, if you project it on the celestial sphere, you will see some point here, and this point, this angle is measured, this is the declination of the test antenna. So when you substitute this, you can get the XYZ from the relationship between these two. So I will just read it. A reference antenna is the origin C. Position of all other antennas are determined as X, Y, and Z. D is a position vector, baseline vector from reference antenna to any other antenna, making the hour angle H and declination D. These are the formulas, and then using the used for determining relative the positions of I mean this the should not come here, relative positions of antennas within an antenna array of a radio telescope. Okay. Now this one, this diagram should have been brought slightly later, but I brought it earlier because it may be easier to understand. Now, if we see, there are two coordinate systems in this one. First of all, let me explain this one. This is the part of the celestial sphere. Your astronomical object is somewhere here. If you expand the astronomical object, you can see that the intensity distribution will form these contours. And on the other hand, you are on Earth at some plane. Your antenna will beam shape is like this, which is looking at the central point of this one. And you will have to measure. You have to relate this this coordinate system, that is L, M, and N. L is circular along this direction, M is circular along this direction, and N actually is along this direction. And we have another coordinate system where our antenna visibilities will be lying on this plane. Actually, when I go to the mapping techniques, there you will see that this is the aperture plane, that is the aperture of the collective antenna. Collective antenna means you have collected data over several hours, and that forms a plane in which you will put it, that is called the UV plane. And because those data are there, those points are there, you can construct a antenna there. That is a pseudo antenna, but it is really for making images you require that one. So this is the beam of that antenna. Now this is called the UV plane, and this is called the LM surface. Now actually, if you see, we are actually this surface is spherical like this, and the actual point may be P, but we consider it as here, and there are little bit of error in that. This angle is located here, you can see. I just read this one. This is not very important right now because you will not be able to understand until I explain all those things, but this is just a glimpse of this one. I'll just go to the next slide, but before that I'll read it. Scanning a radio source located on the celestial sphere using a tracking antenna. Approximation of the actual field point P dash to P. This is about this one, and you can see these are the approximations for L coordinate and M coordinate. Now this is a slightly extension of that one, the UV-W coordinates which I have spoken about. You have this one in the previous direction. The W coordinate will always point to the source, and UV is the plane in which the aperture of the collective antenna or the giant antenna lies. Now if you relate it with the XYZ system, so this is your source. As I said, the W axis will be pointing to this one, and this you can see, this is the our angle. This is the celestial equator and meridian of the reference antenna. Now the W coordinate is always directed to south S, and U always lies on the equatorial plane. So this U coordinate will always lie on the equatorial plane. We are not putting it, but it actually happens. When you get the data, you will see that this will be always be in the equatorial plane. The UV plane is always perpendicular to the source direction W. H is the local hour angle of the phase reference position of the radio source. Well, the phase reference position is a point on the radio source with which you take it to be as 0 with respect to the local media. Here S is the eastern hemisphere, and so H is negative. Okay, the UV-W coordinates are used by radio interferometers for supersynthesis in radio astronomy, a technique that I will be describing later. So this is not much informative, but this may keep an image in your in the back of your memory. Okay. Now we have a little bit of very little bit of spherical trigonometry, where you are relating the angles of a great circle with I mean you form the laws of cosines and sines and all so on. So now consider this sphere. You are at the center O, and these three axes are perpendicular to each other, forming X, Y, and Z system. This is the right-handed system. Okay, it doesn't matter here. And then over the surface of the sphere, you cut these with three lines. These axes with three lines. One forming a triangle. This is not an exact triangle, a flat triangle, but this is a curved or a curved surface triangle. So we have to derive some relations between these angles and the angles which are these angles. That is, the angles formed between this and the angles formed within themselves. So these are the two laws which are widely used. This is sine A by alpha. That is, sine A is this angle. This is A. And by alpha is this angle, is equal to sine B by sine beta and sine C by sine gamma. If you remember, for the flat triangle, this is sine A by A and is equal to sine B by B and sine C by C, where A, B, C are the angles of the triangle. You can remember this one. And the other one is this cos A is equal to cos B cos C plus sine B sine C cos alpha. So this is also somewhat easy to remember. Suppose you want to measure, you want to find the cosine of this angle, so you call this one. So you have to have cos B cos C. So B and C are these two sides, and again sine B sine C are these two sides. You don't consider this A here, and multiply it with this angle cosine of this angle. So it's very simple to remember. Now you come to the conversions between various coordinate systems. So we have seen different coordinate systems. Sometimes it may be necessary that we have to go from one coordinate system to another. The conversions for each coordinate systems, I think I have done here. This first one is the conversion between locally and universal equatorial system. Okay, these two diagrams match, except that one point is the reference point is vernal equinox, and for the other the local meridian is the reference point. So the declination will be the same, whereas the hour angle relation will be this way. This is the sidereal time minus alpha. The declination delta coordinate is identical among both the systems. The relation between hour angle h and right ascension alpha is given as h is equal to sidereal time minus alpha. This is very easy to remember. Now we go to slightly complicated things. This you need not remember, just I am talking, just listen to this one. The conversion between local equatorial and alt-azimuth system. What you require is, when you are doing actually working, you require these formulas in a matrix form, and then you can have a coefficient matrix multiplied with given angle is equal to the wanted angle in some other coordinate system. So where you can use these formulas. So this is for conversion of local equatorial coordinates delta h to alt-azimuth coordinates. This is the coordinate system, that azimuth and elevation coordinate system, or alt-azimuth. So here this is E stands for elevation, A is for azimuth, and these are related with the declination delta and this hour angle. So you have the three relations where L is the latitude of the place. This is the L is the latitude of that place that you have to put it. And this one shows the conversion of alt-azimuth coordinates EA to local equatorial coordinates. This is just the reverse of that one. So here again you have these relations. I will move on to the next slide. Now again here you have conversion between universal equatorial and galactic coordinates, and I'll just read this one. There is no much explanation to be done in this. Let A alpha g and delta g be the equatorial coordinate of the galactic pole, and alpha c alpha delta c be those of the galactic center. We may relate the universal equatorial coordinates alpha delta and the galactic coordinates L and B, galactic longitude, galactic latitude B, using these relations. And here you can see I have used L omega, L underscore omega can be obtained from sine this. So this is just a matter of substitution. I'll go to the next one. And here again there is nothing much more to be explained here. This is these are the for conversion between equatorial, universal equatorial and ecliptic coordinates. So all these are similar kind of things, and then again you have this in the matrix form, this xyz to UVW. So you want to derive UVW, you just multiply this coefficient matrix with these given parameters, where x lambda is the length divided by the wavelength. So these are very useful when you are doing imaging, and also for some other engineering measurements where you may require these things. So I don't explain it much, because I find this you can. I'll give you the slide. You can take this one. So I will not explain much here. Okay. Now we come to the electromagnetic spectrum. Last time also we showed something about this, but this time you see that this picture again is a bad picture. I borrowed it from some place. So here you can see the entire electromagnetic spectrum. I have to see it carefully, because this is the wavelength. These figures are for the wavelength in meters, and these figures are frequency in hertz. This is the visible range, which has been expanded here and shown, and this side is X-rays, this side is gamma rays, and lower on this side lower frequencies. These are radio waves at longer wavelengths. Now you have expanded this window. This is a portion of this radio window 10 to the power 4 to 10 to the power 11 hertz here. So this is used for maritime and aeronautical uses. This is for amplitude modulated radio, again for mobile radio and so on, FM radio, TV channels and all, and so on. So this is how the spectrum is used commercially. And in general, this is the chart how you remember the various frequency bands. So this is from engineering point of view, we use this kind of divisions, 30 to 300, 300 to 3000, 3000 to 30,000, and so on. That way it goes. So medium wave frequency is 300 to 3000 kilohertz, and you see the wavelength is 1000 to 100 meters, and so on. This is a high frequency. This is a short wave, 3 to 30 megahertz, and this is very high frequency. This is VHF actually, 30 to 300 megahertz. This is ultra high frequency, or UHF, 300 to 3000 megahertz, and SHF, super high frequency, 3 to 30 gigahertz, extremely high frequency, 30 to 300 gigahertz. You do have subdivisions in between, like K, X, L, Ka, Ku, and many other bands, subdivisions of this. But these are the general divisions in which you can remember this very easily. Okay. Now we go to the transparency of the electromagnetic waves. Now we are gradually entering into the engineering thing. In between some astronomical things will come in, but this is a technical course, and radio astronomy is fully technical. Except the users use it, they may not be interested in knowing all these things. But if you want to make a telescope or something like that, I think this is what is required, including imaging, because image processing may be done by somebody without understanding what is happening inside. Engineers make those algorithms and implement them. So this is about describing how those things are made. So I'm just gradually going into the more of engineering kind of things from now on. So this is the atmospheric transparency of electromagnetic waves. This was a measurement taken way back, Giacconi et al., 1968. So this axis is about frequency in hertz, and this axis, the y-axis, is about altitude. This is the ground. 0 is the ground, or the sea level, you can say. And as you move up, what happens? Now this portion, this gray, this dark portion, grayed portion, this is where the electromagnetic waves gets absorbed. So that means, for example, at this point, if you see, this is at a height of say some value over here, and at this frequency. So if you go above this particular height for this particular frequency, you will be able to receive the radio waves. But if you come below this, you will not, because it will be absorbed. So this diagram means that. This is in the logarithmic, the fraction of atmosphere. That's the total atmosphere, and how much fraction of it is there. You log of that one, so it's coming in negative numbers. So this diagram is very important, because this actually describes the windows in which you can actually make your system work for radio astronomy. If you are located somewhere in between, you will not be able to get the waves. So from that angle, this is very important. So this is another version of that one. Here you can see that this grayed out portion is called the opaque, and where this white is transparent. That means outside radio waves can come to us through this. These are called the windows of the spectrum. This again is a spectrum diagram. Here you can see these are gamma rays, X-rays, ultraviolet. These are totally blocked by our atmosphere. And again we have an optical window here which actually comes to us. Then in between we have several windows. Sometimes it comes, sometimes it doesn't come. And then we have a large window over here. This is called the radio window. This is about the plasma frequency, that is around 10 megahertz. I think that is the plasma frequency. I will just yeah. So we go to the next slide. This is about the signals that we receive. Actually, the radio astronomical signals, as such, they are not signals described in engineering terms. We call signals that is well-defined combination of sine and cosine functions of time. These are the actual signals description. But then we also describe this kind of signals that come from the various astronomical sources as noise. But here we will consider it in the reverse way, because we are not considering the communication part, communication signals. We are only talking about the noise generated by extraterrestrial objects and noise generated by our system. So we consider the extraterrestrial objects noise as the signal and the noise as noise. Now this is the functionality of a this is the probabilistic distribution of noise occurrence. It's a very simple diagram where mu stands for the average noise. If you see the variation of a particular thing, I call it, let it be a noise. The noise can vary in positive direction and negative direction, and this is the probability of occurrence. That is the probability density function, P of x. So it is centered here. So on both sides you have equal probabilities. So that is why mu is 0. And sigma is the standard deviation, and sigma square is called the variance. We have for 3 different type of distributions. So you have these values here, and this follows this formula and this probability density function. You can see it. I don't need to read this one, and I will just read this one. Most of the radio astronomical signals have random fluctuations of amplitude and phase. They have a Gaussian distribution. They are randomly polarized. Gaussian probability distribution for 0 mean and 3 different variances are shown. So this is what it is. For 3 different variations, we have 3 different curves. This is also known as the bell-shaped curve. Many other normal distribution, many other names are there for this one. So what I want to say is that any signal that you receive from the sky, that will be of Gaussian noise kind of characteristic that will have. So if you want to see the actual signal, you can see this one. So you have a telescope here, or an antenna whose beam is like this. It is pointed towards this. It's just standing static. Now we have 2 radio sources. Over a period of time, they will be moving from east to west, and they will cross these beams. So when this is more powerful than this one. So when it crosses this, we have a peaking in the received signal, and when it crosses this one, again we have a smaller peak. So this is the one. This is the time in which you have received the signal. So you can see this is the system noise. This is spectrum analyzer noise or whatever it is. When the bigger object was on the beam, you have an amplitude increase, but still it is a noise. It is not a well-defined signal. Then again you have noise here, and this is when the smaller one crosses this one. You have another noise-like structure here. This is called the drift curve from 2 radio sources. This is the celestial sphere. Okay, I'll just read it. 2 radio sources, strong and weak, producing a drift curve when they cross the antenna beam. So whatever signal you get from them actually are like noise. Now this is for entertainment. Some radio astronomical sources, Cassiopeia A. This is one of the sources that we use for deflection tests and all. I think you people may be doing it. So this is actually a supernova remnant. About 300 years back, this supernova took place, and it is a very wide angular source. I have not talked about what angular resolution and other things means. That will come later. But what in general sense, you can see that the beam width of the antenna is maybe smaller than the extent of the source. Then you can call it as it's all relative with what instruments you are measuring. It's not fixed. So if you have a very wide beam antenna, you call it a narrow, point source or something like that. It's all relative terms. So I'll just read it. Cassiopeia A is the remnant of supernova explosion that occurred 300 years ago in our galaxy at a distance of about 11,000 light years from us. Cassiopeia A is one of the brightest radio sources in the sky and has been a popular target of study for radio astronomers for decades. The material that was ejected from the supernova explosion can be seen in this image as bright filaments. Okay. This is at the end part of a star when the fuel ends. That is, in the star generally it starts with hydrogen fusion, and then when the hydrogen ends, it goes to helium fusion, fission. Fusion is what takes place in a star, this kind of nuclear reactor. And then it generates carbon, nitrogen, oxygen, and so on. And then the core gets more and more intensified with heavier elements. And then a time comes when the fuel of the star completely ends. And at that time, the gravitational pull will cause it to collapse. And because of this, a heat will be generated inside, which will cause it to expand and cool. When it expands, it cools down, again it comes down. And after occurrence of certain times, depending on the size of the star and many other things are related to that, it will just explode. And that explosion will be the energy of that explosion is you cannot count it. It comes in some 10s or 14s of exponents. So it's very difficult. You cannot expend, you cannot use that energy, you cannot imagine how much energy it is. So this will distribute all those elements that are generated in the star. From hydrogen it will create different elements gradually over the years, and finally this explodes. And in the process of explosion, these elements actually get spread out in the region, and again new stars and planets will be formed, and then whatever we get inside a planet, some metals and all, they are actually coming from the stars. The stars are factories which create elements. I will put it in very short. So, so this supernova explosion, after the supernova explosion, this will and the final destination of the star could be, it may become a white dwarf, or it can become a neutron star, or it can finally, it depends on the size of it. That's Chandrasekhar limit 1.4 solar mass or so. So you can see all those things. This comes in astrophysics and all. So what is important here is this picture is a gradually expanding ejected out material from the star. So its size is increasing. Day by day, its size will be increasing, and this has been taken as 1.4 gigahertz, 5 gigahertz, and 8.4 gigahertz. It's a combined image, and this has been taken from NRO. Now, this is another supernova explosion that has been recorded over time. So I don't know whether you were able to see this diagram. Let us say I am not able to see it very clearly here. Maybe this is 17th May 1993. Is it that what it is written? Yeah. Okay. Then you see this is at a later date. This is at a later date, and so on. So they have taken snapshots of this one, and they have found that the this is also a supernova exploded material. I'll give it background. Radio study of supernova SN. SN stands for supernova. This will be the catalog name for this one, SN 1993J. This gives you the year in which the supernova occurred. Located in M81 spiral galaxy at 11 million light years. Images constructed by very long baseline interferometry. I will talk about VLA later on. This technique is very important, and there are limitations for this. So I will talk about it. Images constructed by very long baseline interferometry using VLA. VLA is a radio observatory. You know that NRO owns this in New Mexico. They have, and various tracking stations around the world. The sequence of images are constructed by observing the regular intervals. It shows a shell-like radio structure that has expanded for 7 years with circular symmetry. So what it means that it maintains its shape but increases its spread out. The color scale represents the brightness of the radio emission, with blue being faintest and red as the brightest. Now this is something about the cosmic microwave background radiation, CMB. So if you look into the sky at empty space, you will not be able to see anything unless some astronomical objects or lumped objects falls in it. I am talking about where there are no lumped objects. If you look into that sky in any wavelength, you will not be able to receive anything, except in radio. You will be able to get this information all around. Here you can see that actually this was an experiment conducted by Arno Penzias and Robert Wilson with a giant radio horn, and they got the Nobel Prize for this one. And it shows that there is radiation of at the temperature, black body temperature of this radiation is 2.73 degree Kelvin at present, and this has happened because of expansion of space, as I was talking in the last lecture about this. Something I was saying, I don't remember exactly. So here you can see the actual distribution should have been uniform. This is likely to be in the galactic coordinates. The coordinates are not given here, so we cannot say which it is, but it seems to be like galactic coordinates to me. So you can see that still there are some issues, like it is not very uniform. These colors shows that there are these are intensities are varying, but this has been expanded. This is not as much as you think. It is very negligible. It is expanded out. So it's more or less uniform, but still there are some lumped parameters here. This shows that the structures were forming during the process of evolution of our universe. I'll read this one. With an optical telescope, the space between stars and galaxies, the background is pitch black. But with radio telescope, there is a faint background glow, almost exactly the same in all directions. That is not associated with any star, galaxy, or other object. These are the lumped elements that I was talking about. It is the cosmic microwave background radiation and was discovered in 1964 by Arno Penzias and Robert Wilson. Now, here again for some of your entertainment, I will present this one. This is some radio astronomical sources in which you see the sun at 1.7 centimeters wavelength. Here it is. You can see this one. I will first read this one, then I will go for explaining this one. The radio waves penetrate through the outer layers of solar gas, chromosphere and corona. This corona and all I have explained here. I have not explained, I mean, from the person whom I got this diagram, he has explained that. I obtained it from internet, both these pictures, so I am thankful to them who has put it up there. The penetration depth depends on the wavelength. The image shows that the structure of the sun atmosphere near the transition region between the chromosphere and the corona is about 2,000 to 2,200 kilometers above the photosphere. This chromosphere, photosphere, they are different layers of the sun. The photosphere is that layer from which we actually get the light. The chromosphere is a layer slightly above that, and above that there is the coronal region that you will see here in this diagram. The right diagram gives the correct picture of the different layers. Okay, here it is. This is the structure of the sun. Here, this portion is called the core, as explained here, and this is the radiative zone. And then this is convective zone, because from this radiation, these radiations actually travel to this one after many thousands of years. That process is called a random walk. in which it actually exchanges energy with other particles, and finally its wavelength will be reduced, and then when it comes out it will be at some different wavelength. This process is called random walk because the particle goes in various directions, hitting each other, and it comes out, which is responsible for the radiation. Now you can see that this kind of structure, this is called the prominence, and the external thing that that is in this shaded this particular thing, this like looking like hairs coming out. This is the corona, and this is your photosphere, this layer, in which you can see the sunspots. The sunspots will be visible in this, and this is the layer from which we actually receive our white light. Now these structures that you can see, these dark line-like structures, curvy line, they are called filaments, and this portion where there is no corona, this is called the coronal hole. So I will come back to our more of engineering things coming from this. Yeah. Now this diagram is very important. I don't remember the person's name who created this diagram, but then this is useful because it gives you an approximate measure that what you are going to measure, what type of signals you are going to measure from the known sources. So this is some kind of estimation. So here you see this axis, you have the wavelength, so running from 30 meters to 0.01 meters, and this axis you have the flux density in Jansky, that is watts per meter square per hertz, 10 to the power minus 26. 1 Jansky is equal to 10 to the power minus 26 watts per meter square per hertz. And this measurement has been taken with a 3 meter square aperture area antenna. So this chart is available everywhere in the internet. You may find it somewhere. So these are the known sources. For example, our sun gives this kind of radiation. If you measure this radiation at 3 meter wavelength, 3 square meter antenna, you will get, for this particular wavelength, you will get this kind of value, output from the antenna. Now towards the galactic center, if you look, it will be having a this shift. You can see that this is falling in a very straight line kind of thing, but this scale is logarithmic, you can see. Then this is human generated noise. This consists of alpha and other things. Jupiter also generates noise by synchrotron radiation. You have from our galactic center also we have synchrotron radiation and so on. So and this is a quiet sun radiation. This is the active sun. Active sun means a period in which the sun becomes very much active, increasing mass ejections and radio radiations, ejection of particles and many other things. This comes in 11 years cycle. 11 years is a half cycle of it. The full cycle is 22 years, and around 2011 it should have reached one of its peak or peaks, one of its peaks. It should have reached. I don't know whether people are receiving anything or not. Then we have radiation from this moon's radiation in this wavelength, because this acts all of the objects that are outside, they have some temperature, and due to that temperature they will be radiating like following the Planck's law. And if you go to the lower end of the spectrum at lower frequencies, there you will see that the Planck's curve doesn't come to a halt, but it goes on, except that the power comes down. And that is, the radio emission will always be there. Anyway, I'm going to those to the Planck's law. It is very important. We will go to that later, and so on. So there are Crab pulsar and all these things you can see in this slide. Now we go to the basic mechanisms that are responsible for radiation. Last time we left it out at this place about thermal radiation, non-thermal radiation, and thermal radiation is basically the Planck's law. When you hit an object, it radiates in all wavelengths. The intensity of radiation at different wavelengths are different, and the peak shifts with temperature. So there is a quantitative relation, that is Planck's law. And non-thermal radiations are can be like synchrotron radiation, where a charged particle moves around having a velocity, gets trapped in a magnetic field and keeps rotating around, spiraling around the magnetic field lines, and thereby emitting radiation. That is called synchrotron radiation. Bremsstrahlung radiation is something which happens in plasma and all because of the movement of charged particles due to heat, and it's also sometimes called thermal Bremsstrahlung. I don't know how to pronounce this one. So here it is. This is the Planck's law. If you see here, I have you can see it is marked in wavelengths, nanometers, and this is the visible wavelength. So if you heat an object to certain temperature, then it will radiate following this curve. So if you heat an object at 6000 degree Kelvin, for example, our sun is around 5800 degree K, 5800 K. So it emits white light from the photosphere, you can see, and you can see this is the spectral radiance. This is in watts per meter square per steradian per hertz. Steradian means within what angle it comes, and what is the energy per unit time, joules per second. And you know, this is the area in an area, in an angle, and per unit bandwidth. I didn't explain this because I somehow skipped that slide. Later on, when I went home, I just saw that because of my mouse clicking, that slide went up. Why this is measured in per hertz, and distance parsec, I didn't explain it last time. So I will do it at the end of this one. If I don't, please remind me. Now, this is the spectral radius. You can simply think of the intensity output of the radiation. That way you can, just to simplify things, you can remember it that way. So you see, if you heat an object at 6000 degree Kelvin, it will radiate maximum amount of radiation will be in the visible region. If you heat it at 5000 degree Kelvin, you can see the peak is shifting from this one. It is shifting to the right, and also the intensity is also coming down. This is at 4000 degree Kelvin, you can see. So this is the reason why different stars have different colors, because due to their size and due to their temperature, their color also changes. And O, B, A, F, G, these are the type of stars that come in play. Whereas G star is a very lower end star. Our sun is a G star, G2 or something like that. I don't remember the exact number of that. So there are stars which are much bigger and hotter than the sun, which emits in different wavelengths, in smaller wavelengths than visible. If you see, the Planck's law doesn't come to an end here. It keeps on traveling, and it's asymptotically you can finish it up somewhere, but then it keeps on traveling and it doesn't end. So at radio wavelengths, these things come down to very this intensity of radiation will be much less at radio wavelengths. Now there is a law for determining this peak intensity, that is Wien's displacement law. We will see about it, and also you should know that whenever we are catching in radio some like I said last time, that from moon or from some other object also we are getting radio wave radiations. So those things we are catching because of this, because we are catching it in this region, somewhere much lower than the actual object temperatures. Now these are some of the formulas which people use very often. This is the Stephen-Boltzmann's law. This is about flux, and you can say that the flux of a black body that is the amount of power per unit area it radiates, is proportional to the fourth power of temperature. So if you increase the temperature, the flux increases T to the power 4 times. So this constant is called the Stephan-Boltzmann constant, this sigma. And this has a fixed value. This is something, for this particular equation where you want to get the flux in watts per meter square, there this is the value, sigma is equal to so and so watts per meter square plus k to the power minus 4. So here temperature should be in Kelvin. So then only you will get flux in watts per meter square. Then again comes the luminosity of a star. It depends on the size of the star. It is just a formula of a circle. Pi r square is the area of a circle, if I remember it correctly. So you can see the luminosity is proportional to the radius of the object, radius square of the object. This pi r square term is coming here, and then for some multiple, and then this sigma, this Stephan-Boltzmann constant, and T to the power 4 relationship. So this is calculated in watts. What you are doing is you are actually multiplying it with area, this particular thing, and you are removing this and getting only watt. This is it. Then comes the Wien's radiation law. Wien's radiation law and Rayleigh-Jeans law. You can see this and this. These are actually approximations of the Planck's law in two sides of the spectrum. That is one on the higher end, one on the lower end. Lower end means lower wavelengths, lower frequencies I am talking about. Lower frequencies is this Rayleigh-Jeans law, that is at radio frequencies. This actually approximates the Planck's law. And this Wien's radiation law approximates the Planck's law at higher frequencies. I will show you the curves. For radio astronomy, therefore, we use this one rather than Planck's law, because Planck's law is complicated. As you can see here, this has a complicated expression. So instead of that, this Rayleigh-Jeans law comes very handy, and this also is used in communications and all. Many places we are using this this expression, this Rayleigh-Jeans law, in receivers and other places. Now, as I said, the Wien's displacement law actually finds out the peak radiation intensity, radiation wavelength. For a given temperature of the black body, it will indicate what is the wavelength of peak radiation. For example, for this curve, if we calculate, it will give you this 483 nanometers. So you can see that lambda peak is equal to something divided by T. T is the temperature in Kelvin, and this comes out to be in meters. Now, as I said, Wien's displacement law, this is about brightness, and the Planck's law is also about brightness V. Okay. So this you can see it is a simplified expression 2h nu divided by lambda square. Nu is the frequency, lambda is the wavelength, h is Planck's constant, and E is the exponent, and you can see that K is Boltzmann's constant, and T is temperature in Kelvin. Nu is frequency in hertz. So this comes to be watts per meter square per steradian per hertz. Similarly, Rayleigh-Jeans law, you have V is equal to 2 kT divided by lambda square, watts per meter square per steradian plus per hertz. Now there is something called apparent flux, apparent brightness, you can say actually. That is the observed brightness or observed flux or whatever it is. So flux will be in watts per meter square, and brightness will be watts per meter square per steradian per hertz. So the two units are different. So anyway, so I am just calculating here for flux. And so this is in watts per meter square. So F is equal to luminosity L divided by 4 pi r square, where r is the distance from the object to us. It's not the radius. This radius is this is the radius of that object. This is the distance, and you can see that this simple expression 1 by 4 pi r square. This is the inverse square law of radiation. If you remember it from your electromagnetics. As I said, the approximation of Planck's law with these two laws. See, this is the radio range. This side is the radio range, and this side is optical and higher frequencies. So you can see the Rayleigh-Jeans law is an asymptote on the radio range. This one. And the Wien's law doesn't. This is the Planck's law actually. So Wien's law doesn't approximate the Planck's law. Planck's law is the correct form of radiation law. These are Rayleigh-Jeans and Wien's law are only expressions, what you call that, approximations of that. And Wien's law, you can see that it follows exactly on the other side. This is in normalized frequency. I have not given a particular frequency, but only to show you here, and this normalized intensity. Then, as I was talking about the Planck's law, now this is an example of the sun where you can see the spectral radiance is given here. So brightness, you can say this is the brightness on this side, and then wavelength on this side, and you can see this is the spectrum of the sun that we get from the sun. So this the sun is approximated as a black body at 5,800 because that is the temperature of the photosphere, and reasonable range is 10 to the power minus 7 to 10 to the power minus 3 meters. So you can see that where is the 10 to the power minus 7 is something around here below the ultraviolet, and 10 to the power minus 3 will come somewhere here. So if you draw two lines on this way, you will see that this is the curve we are getting. So this curve, you see, it looks like a Planck's law. Whereas these portions are not very stable because the suddenly causes disturbances in this region, and you will get, especially during this 11-year half cycles and all these disturbances increases, and it no longer you will be able to follow this curve, but you will see higher emissions at these frequencies, and they are temporal emissions. They remain over a short period of time and unpredictable with time. These are the region of flares where you get solar flare, and here you get large bursts in this gamma rays and X-rays region of flares. So if you want to approximate the sun as a black body, you have to approximate it within this frequency range. Now, as I said, the synchrotron emission. We have covered the thermal now. Now we go into the synchrotron emission. It's a simple law of force. If there is a charged particle Q, if it is moving along this direction with velocity v, and you have a magnetic field B along this line. So, if this velocity is not zero, then the particle will be subjected to another force, which is the result of its movement along this direction in the magnetic field, and that force is along this direction. So if you try to move along this direction, it will also pull you in this direction. So this can be this is related by the right hand rule of vector. So right hand screw you can think about. So if you here it is given v cross b, where v is the velocity. This is a vector quantity, and b is the magnetic field. That is also vector quantity. So if you cross it, so you take the right hand rule. So v cross b, and if you take the spiral around, so you will see it will go this way. That is the right hand screw rule. So that is F. So the force acting on that charge, another external, another force that is generated because of its motion is F. Now, because of that, the final motion of the electron will be something like this. See here, this is the magnetic field, this B along this direction, and here you can see that the electron is spiraling around it. It will be spiraling, because when it tries to move in direction, it pulls it in this direction. Again, when it tries to move, it will pull and it will make it rotate around that one. And on the process, it also radiates. And this radiation, the polarization of this radiation will be parallel to these circles. Okay, here is the electric field. Electric field of this will be parallel to the circles. The magnetic field, this is the magnetic field of the electromagnetic wave, not this magnetic field. Okay, so the electromagnetic field, magnetic field will be in the same. So this is the wave front. You can see. So I'll just read it. A force on a moving charge in a magnetic field is equal to cross product of particle velocity with magnetic field times the magnitude of the charge. Q is the charge. An electron at relativistic speed spirals around a magnetic field line, resulting to synchrotron emission. It is polarized with electric field parallel to the shortest distance between the electron and the magnetic field. This is the description. What I in words it is like this, but this is what I explained right now. Now here some examples are there. These are not actually radio figures, but still this figure on the left you can see that the bluish glow from the central region of the Crab Nebula. This is a kind of a nebula. Nebula is some sort of gaseous form of thing in space. You can read more about nebulas in Wikipedia and all, and you will know what is a nebula. So Crab is the name of this particular nebula, and this bluish glow, it says, is because of synchrotron radiation. This picture I got it from the perhaps from the Wikipedia or somewhere, but from the internet only. And this is definitely a Wikipedia picture. So this is for the AGN stars. AGN stars are the active galactic nucleus or something like that. It is not a star; it is a galaxy, and the central portion of the galaxy radiates at very high intensity. It's much more intense than hundreds and millions of stars sometimes, and its wavelength also are very broad, a broad range of bandwidth it radiates. Actually, because of some maybe I don't know, because all of these objects do not radiate. We did not receive radiation for all wavelengths, but people still believe that these radiations it radiates in all wavelengths, and we are not able to receive these radiations because some gases or some other things in the interstellar medium or intergalactic medium they may be absorbing it. So here is this one. This is called the AGN. And yeah, here you can see there is a very powerful jet, energetic jet, HST image. The blue light from the jet emerging from the bright AGN core towards the lower right is due to synchrotron radiation. So they are telling that these radiations are due to synchrotron. Synchrotron radiations are more powerful, and you can see the features more of this in internet if you like. You can refer to that. And then the final one is that Bremsstrahlung radiation. It generally happens in plasma. In plasma form, you have separation between ions and electrons, and a slight disturbance causes the movement of the lighter particles. And when there is a movement of these particles, there is bound to be a radiation. So here, and the movement can be caused by some ray falling on it or something which heats the system. If you heat a plasma, then the electrons will be randomly moving around, and in the process, it will also generate this phenomena. and it's here I have written it here. It is the electromagnetic radiation produced by acceleration of any charged particle when deflected by another charged particle. So here you can see this some of these particles. This is a heavier particle. These are the lighter particles. They will be going along this. It tends to go straight, but because of this, its path moves, changes actually, and this change of the path causes it to accelerate and deaccelerate in a direction which is which will be along this direction. Because this velocity you can divide it into two components, one along this direction and one along this direction. So that way, and here you can see that the velocity which is along this direction, that will be having a change of velocity with time. So that means there is a acceleration, deacceleration in that direction. So that causes the radiation to come. Now, if here it is, it has a continuous spectrum. A continuous spectrum will be there because there are several of these, and all of them are causing. It's not just one or two particles, but many are there. It continuously happens in a plasma from mechanical interaction of free electrons with ions. In a uniform plasma with thermal electrons, the power spectral density of Bremsstrahlung radiation is given as, well, you don't have to go into very much details of this. These things you can always find from books, and maybe we may not be able to use this in our applications, but this just for knowing it. And here these relations come from here this dP by d omega. D omega is the change in frequency and dP is the change in power. That is the expression, and this is proportional to this Ne. Ne is the electron density, and Re is the electron's classical radius. Me is the mass of electron. Kb is the Boltzmann constant. Ge is the electron's temperature, and Z effective is the effective state of ion charge. So what we are trying to find out from here is we may be able to show some kind of spectrum of this radiation. So here it is. Again, this is a more simplified diagram. You can see that this electron passes through this. Z is the okay, an electron E bar an electron E crossing an ion with charge Ze plus undergoes a non-uniform acceleration deacceleration, resulting in Bremsstrahlung emission of photons. This must be the core of the atom, which may have more number of charges. So that is why this positive charges, that number of positive charges is equal to Ze plus, where Z is the number of protons in the nucleus. Now, here is a tentative plot of the Bremsstrahlung spectrum using arbitrary units. This is the frequency, and this is the dP by d omega. Here you can see that the variation is this way. It drops somewhat like exponential. Now, this is the Bremsstrahlung and synchrotron radiation from the spiral galaxy NGC 925. It's an example. You can see that here this is this side is the frequency, and this side is the relative flux density. So this somewhat normalized kind of thing you can say. These are the type of radiations that come from this galaxy. The portions these are due to Bremsstrahlung, and this is due to the synchrotron, this long one. Synchrotron radiation are generally asymptotically straight, something like this, with logarithmic scale, and then in log-log scale. and then you have this Bremsstrahlung plus synchrotron, this radiation. This is just an example that this kind of things we are dealing with in radio astronomy. And this is the picture of a soft X-ray thermal Bremsstrahlung coronal image of the sun, taken by this particular observatory on so and so date. It highlights the magnetic field loop structure that forms the precursor environment of the solar flare activity. So this is just for your entertainment. You can see this, and I will okay. And this is the last slide, and we come to the end of this presentation of lecture 2. Thank you. And before that, before I really end this one, I will give you the slide which I missed last time. That is, see, yeah, here. See, I said that one astronomical unit is equal to this and so on, and I have not explained this parsec and megaparsecs. So here is the explanation. And also I didn't explain that this unit, where is this? Yeah, this watts per meter square per hertz. Why we are interested in taking it per hertz? So if you see what is a parsec, well, if you see our solar system, you will see our position. Earth is rotating, revolving around that sun. So the average distance, as I said, is 150 million kilometers. That is one astronomical unit. Now, if you see a star, which is a nearby star, then you will see that the position of the star seasonally changes, because there are stars which are much farther away from us than this one, and we will observe this star to be moving in this region, in that constellation of the stars. This is because our movement is along this direction, and when we see this star, we see this as the background. And after 6 months, when we come here, we see along we see the star with a background of another star here. So trigonometrically, we can calculate this distance d. So this distance, we know that we know this distance. We want to calculate this distance. We also know this angle. This angle is called the parallax angle, P. This angle is same as this angle. So you can relate it with tan theta, or tan P is equal to 150 million kilometers by d. Now, it is difficult. I mean, some people, astronomers, they feel it difficult to give figure-wise distance and all. So what they do is they just keep it in inverse of the angle. In this case, it is in arc second. So you can see that d, actually, if you remove this PC, d should be equal to this one astronomical unit divided by tan of p. It should be actually. But then, since this angle is very small, so tan theta can be approximated to theta, and this is how it comes. So this d is equal to 1 by p, and p should be in arc second. This d is the parsec, that is the unit. So with this, I come to the end of this lecture 1.